tankers route to the U.S., Middle East, South America, as well as Europe. Northern Europe is one of the major oil production, crude oil. So it's a big problem, but just to give you an experience, just to make the long story short, we have a very big problem because we have discrete demand. Demand is not constant. If demand constant, you can build a constant time model. Demand is not constant. It's a long-term planning. You talk about 60 days to 90 days. You have, if you talk about industry people, they don't care of what's the cost. They don't care. All they care is the cost per gallon, right? So or the cost per ton of importing the oil, so they can put the price tags on when they sell the refined oil. So it's become very difficult problem. Talk about 2-month scheduling, given daily production profiles. The company has to manage a fleet. Sometimes you have what they call is opportunity ports, like a different oil company has excessive oil, so they might want to buy it, pick it up. So it's a very difficult problem, and you can build this gigantic model to solve it. It's not linear. We put in simplex, it cannot solve. And this is a real life problem. After 20 hours of big cluster that we have at ExxonMobil, we couldn't solve. There's no integer solutions. So we came up with aggregate the demand using sophisticated vendor decomposition, Lagrangian relaxations. As it turns out, the simple way to do is aggregate the demand, find the approximate solution, and you can solve the problem within seconds. But this is what industry look for. They don't have time for us to do the research and publish paper. So there's a big gap, but somehow if we can sort of solve the larger problem better, then that could go to industry further. So anyway, so I think I'm pretty good with time, and I would end my talk here. I'd be happy to take questions.
Thanks a lot. It's very impressive amount of work. And I think one question I have is that when you're trying to optimize, okay, I know that this is for the maintenance purpose, and you make a flight string and flight schedule. So by any chance that you can introduce some sort of demand model? For example, the objective function now is to minimize the cost, right? Right. But let's say that if I have to adjust my schedule, then you have competition with the other airline and stuff like that. Then instead of minimizing the cost, can we just maximize the profit?
Right. So actually, I wasn't clear. We minimize the cost as well as maximize what we call through value. So based on the demand, if let's say you fly from JFK to LAX, and you have to connect in Dallas. So we would try to introduce, basically we try to put the flight from JFK to Dallas and Dallas to LAX with the same aircraft. So meaning that when you change, you don't have to change the gate. Basically, you just get out of the plane and you get back in. So that's good for customer. We somewhat do it indirectly. But you're right. I mean, if we have more accurate demand of the OD pair, of course, then one can really utilize it. But right now, it's a through value. It's somewhat indirect based on the connection. But if you have second order or third order of the connection, that might be good. And the other thing is, right now, the airlines, they don't share seats. So if they do, it's going to be a very big problem because, I mean, a good problem. I mean, you can save the cost. But in terms of optimization, you can think about how to share, how to exchange the aircraft. That would be really interesting. Yeah.
Okay, thank you. Maybe another questions. I just realized we have a lot of common interest in the research, and the projects that you presented are very interesting indeed. I have a number of questions, but I just keep that for later. So maybe a few questions now. Sure. In your weekly maintenance model, it wasn't clear whether or not the fleet assignment was done before or simultaneously. Because, and if it is done before, does it have to be also weekly fleet assignment?
Right. It's simultaneously.
Simultaneously?
Simultaneously, yeah.
Oh.
So when I present the model, I present the tour alone. And then I show the integration later, because I don't want to belabor you with all the integration.
Okay, so in the weekly model, the fleet assignment was done simultaneously.
Right.
So that means that, but that doesn't mean that the schedule has to be repeated every day, right?
Right. That doesn't have to be repeated every day.
Okay.
And basically, what you do is you introduce one dimension of the fleet, and you can have a matrix where you can tell that this fleet can go with this flight, so it's make the model even smaller.
But would that be a problem if in the schedule we have same flight that appears every day of the week,
Right.
but then on different days you have different aircraft,
Right.
different fleet, I'm sorry,
Yeah.
different fleets. Does that happen in the solution?
Different. We haven't looked into the details of the solution.
Okay.
Yeah, but that's a good point. I think it's something we should see of how the fleet being assigned.
Right, because
Right.
that weekly fleet assignment problem has been there for
Right.
ages.
Right.
But then one of the main counter argument was that in the field they don't want different fleets to be assigned to the same flight every single day, because the comparison they made was that suppose you are a student or a teacher, you don't want to go to different rooms every day because that would be confusing for the
Right.
mechanics on the field. So I just wonder whether that.
I think we can introduce some sort of equity, like how the utilization.
Yes. Yeah, something like
somewhat
that.
similar. Actually, the whole logic should be very similar to the equity of the airlines.
Yeah.
Somewhat. Yeah, but that's a very good point. Yeah.
I agree. Okay,
Thank
great.
you.
Thank you. So maybe we can give a big round of applause to Professor Art for sharing with us his very interesting works. Next speaker is Professor Dr. Ekashai Sumali. He is currently at the Hong Kong Polytechnic University, but he is another Thai that has been going abroad and having a very good career abroad. His education is from, I have it somewhere here, University of Leeds in the UK, and he's been assistant professor at Hong Kong Polytechnic Universities for a few years now, correct?
Yes. Thank you.
3 years?
5 years now.
5 years now.
Yes.
Okay. So he will be talking to us today about online deployment of stochastic cell transmission model for traffic state estimation and prediction. So please join me in welcoming Dr. Ekashai on stage. Thank you.
Okay, thank you very much, Dr. Manoj, and good afternoon. So I'm going to bring back everyone to the ground. Okay, so we are not talking about flying out anything. So this is just something that everybody experience every day. So thanks again for the invitation. And when I got this invitation, the challenge is that can you talk about something that related to research and somehow something that a little bit practical, and that's actually posed a very serious challenge. Because like Dr. Art just said that most of the time when we are doing our research, the real world is, it's not like the main constraint, okay? But eventually I pick up this work that I've been doing with my PhD student, and now he already graduated, Dr. Rensin Chong. And what we did is that we look at a very critical problem of the state estimation, okay? Which is a main component for any kind of intelligent transportation system, okay, that we need to implement in highway management or expressway management. So what I'm going to do today is that I'm just going to give you a quick introduction of what exactly the traffic state estimation is about, okay, and why we need this for the intelligent transportation system. So the short term is ITS, okay. This is a particular piece of work that we start as a research project that we developed this model called SCTM, okay, stand for Stochastic Cell Transmission Model. And the ability of SCTM is for both estimate the traffic state, okay, in the offline version, as well as providing short-term traffic prediction. Okay, short-term traffic prediction means now I know that the traffic condition on the expressway from, I don't know, from Dindang. Okay, this is like now I know how. So you're a tough face, you know. I can't. So if we know the travel time now from, let's say, from here to Dindang, okay, say it's about 15 minutes. No, it's not 15 minutes. It's about like 1 hour. So what's going to happen in the next half an hour? Okay, it's a future, okay, and that's the information that most people want to pay for, right? So if I can tell you now that it will take you 1 hour and 35 minutes, okay, and that's the kind of information everybody can utilize. So we're going to talk about the framework of this and move on to the actual deployment of this so-called SCTM model with the online sensor data. And this is a particular part of the project now we've been doing for the Bangkok Expressway. Okay, so something that shows some kind of transition from research to the actual practice. Okay, so first just a little bit of motivation. So I think, you know, when I give this talk to some other audience in, say, England or I know somewhere else, then I need to motivate them a bit that traffic congestion is a serious problem. But I think with you guys here, I think we share our common experience since we were young. Okay, so traffic congestion is definitely one of the key problems in major city. As well, there are two types of traffic congestion. What we call the recurrent congestion. Okay, something that happens every day. Okay, even I get up, you know, 5 o'clock in the morning, I still need to spend 2 hours to go to school. The other type of traffic congestion is caused by what we call an incident. Okay, so some car crash, you know, some accident happen on the highway, and instead of spending 1 hour, then it's become 2 hours. So both of these pose a serious challenge. And the thing is that ITS, or Intelligent Transportation System, is a kind of framework that tries to use technology, sensor data, information system to help the system manager to handle this situation here. Okay, so if I know that there will be a lot of traffic here, can I optimize my traffic signal? For example, if on the expressway I notice that there is an incident here, can I manage traffic better on the Bangkok Expressway? Okay, so some headline news here is that most of the audience from US probably quite familiar with the congestion problem in New York, and this is what Lensin actually put down. He pretty proud about this problem that they have like 120 kilometer queue, okay, of the traffic in China when there was an incident, and the queue lasts for 9 days. Okay, so that makes us feel a bit better about traffic problem in Bangkok. So then the need is that, okay, we need to get the data from the system on the real-time basis, because we can't think about anything without data. Okay, it's just going to be a guess. It's not the actual expert system. So to get the data, we need to install some kind of sensor. Okay, it can be some camera, can be some magnetic loop detector, can be all sort of things. The problem is that we cannot install this everywhere. Okay, for example, the project that we've been involved, which is the one on the Bang Pri Sukhsawat. Okay, that's the most latest expressway that we have now. They have the sensor, but the distance between each pair of sensor is about 5 kilometers apart. Okay, so that's a big gap. The question is, so what happened in the between? I mean, we know nothing. We only know the data around the sensor location. Okay, there is a problem here, there is a problem there, but how about in the middle? Okay, so that brings us to the problem of what we call traffic state estimation. So this is something that we try to use the sensor data that we have, which may be located quite far apart, and use it to estimate, okay, the traffic condition in between them. Okay, so this kind of information will be useful for all sort of things. For example, we can use for traffic control strategy, you know, route guidance service, traffic management, incident detection and management. So all this is a key motivation of this kind of development here. So this example that I just mentioned here, this is a segment of Bang Pri Sukhsawat highway, expressway. And along this, I think about 30 kilometer expressway, they only have, I think, 1, 2, 3, 4, 5, 6 locations of sensor. The construction cost of this expressway, I think, is about billion baht. Okay, the installation of this sensor probably cost them like less than 100 million. Okay, so the scale of how we actually manage the system and how we actually construct the system is uncomparable. Okay, the money we put so much on construction, is may not actually give you the best solution without any management. So here the question we have is that if you have the traffic sensor detector from this location here along this segment, what happened in this segment here in between? It's about 5 kilometers apart, and a lot of things can happen within 5 kilometers. Okay, so this challenge that we have from this kind of real project. So what we actually came up is that, okay, we need some sort of, like what Dr. Art just mentioned. So when we are faced with challenge, we start with something that we know. Okay, so in transportation field, we know that if we have some data and we want to predict or estimate the data that we don't know, so we built a kind of simulation. Okay, maybe this morning Jay actually mentioned about some sort of simulation here, but the type of simulation I'm talking about is what we call macroscopic traffic flow modeling. Okay, so we do not actually model each vehicle individually. What we do is we define a segment of highway as a block, okay, or we call cell. Then we define a characteristic on how the vehicle should move, or the mass of vehicle should move from one cell to the next cell. Okay, so if there's a lot of vehicle in cell 1 upstream, then of course it's going to take time for them to move from cell 1 to cell 2 downstream. On top of that, what we actually did as a part of the research is that we looked into the actual state of art of this so-called macroscopic traffic flow model, and we noticed that a lot of people use the model which called cell transmission model, CTM in short. And in CTM, everything in any kind of traffic prediction, we assume that everything that we know and everything in the future will be certain. What it means is that exactly in 30 minutes later, I know how many vehicles will get onto the expressway at this point. Okay, or 1 day later, I know exactly how many vehicles will use the expressway segment. But of course, life is not like that. Okay, if I know this, I will not be sitting here and talk to you. I will be some billionaire guy, okay, doing some stock market. So what we do here is that we look into the data and we notice that there are very high degree of demand and supply uncertainty here. Okay, I'll show you this later on. So then we come up with the framework to handle this kind of stochastic demand and supply. The stochastic demand means that we don't know exactly how many vehicles will use the expressway in the next half an hour. On the supply side, I don't know exactly how this kind of performance of the highway will exhibit itself in the next half an hour. Maybe there will be a rain in Bangkok, and we know once there is a rain, everything slows down. Okay, the rain in Bangkok is like glue. Okay, so traffic is actually going very slow. So then we actually try to look into a kind of implementation that linked to the real-time traffic data. Okay, so it's a real-time kind of model. I'll explain what real-time means later on. So this is the overall framework of this stochastic cell transmission model. Imagine you have the expressway. You can think of this expressway in Bangkok here, and normally we will have different sensors. Okay, this gray rectangular that put into different location here. So this is a sensor that actually we detect how many vehicles pass this point and what's the speed. Okay, what's the density? Then this data feed back, okay, directly to the database here. Okay, so we have this so-called real-time measurement. The problem is that this kind of model is very complicated. Okay, it's no linear function, no nothing. Okay, so we just need to come up with some intelligent way to solve this problem here. So the actual research work is how we define this so-called stochastic cell transmission model. It's published in the Transportation Research Part B last year. And what it does is that if you look at this data here, okay, what I mean as a stochastic component. So on the top figure here is the actual traffic demand, okay, on a certain segment in, I think actually in California, okay, I'm not sure where. So you can see that this is on the x-axis here is a time, okay, so 4 a.m. in the morning, 5 a.m., 6 a.m., so forth and so on. And every day is different, okay, every day is different, that's the one thing. The bottom part here is in transportation. We know that the way we define the performance of a certain segment of a highway, we use the density flow relationship here. So if the traffic is very dense, okay, it's very, very high density, then the flow is very low. So the flow means how many vehicles can move from one point to the next, right? So it means it's very congested. So we will have a very, very congested part here on the on the right hand side of you, okay, and the left hand side here is a free flow region here. So as we know that if the traffic is like quite freely flowing, then the situation, the relationship between density and flow is pretty certain. I mean, even though we say certain, still there's some stochastic element here. But once the